think that is about it. So I don't know if there's any questions there, otherwise I can jump straight into doing a simple example of how you might set up a network and what it would look at. So I can't see any questions or hands, so I'm going to assume there isn't anything at the moment. Okay. So what I have here is something called a Jupyter Notebook, and it's just a way to interactively work with Python code. And what happens is that it stores everything in memory as you go along. So it's not like if you were running just a direct Python script and then essentially you run it, and then once the program's finished, all those variables are no longer available. So this just provides a simple way for you to kind of interact, add a bit of code, change it, look at different variables, etc. So what we have here is we're going to start off with the different libraries that you need to import. So for this example, we're going to be using pandas. We're going to use PyPSA, NumPy, Matplotlib, and Xarray. So as a starting point, I just import all those numbers. And then just any custom Python functions that we're going to use in our calculation. So the first is just an annuity calculation that really allows you to calculate the capital recovery factor, and that's what we use to turn our capex into an annualized cost. And here we have a small function that just removes any leap days. So pro tip, in order to simplify your life, always work with 8760 hours. Because often if you randomly have a leap day in your year, it can make things a bit more challenging to keep generic, and now you have to try and match supply and demand, and you need a resource profile that now has 24 hours extra in it. So as a simplification, we always just work with 8760 hours. So the next thing is we're going to want to import some solar and wind data. There are many different ways to do this. So the first is that you might want to import it as a CSV file. So if I run this, what this is doing is Pandas is reading in a CSV file. It's setting the index into the first row, and it's passing the dates. So if I were to print out what that looks like, you can see we have in the CSV file, we have different areas. And if we wanted to, let's plot. So if we wanted to plot what the resource is on the 1st of Jan 2012, you can see that we have now, that's what and this is a unitized profile, so it goes between 0 and 1. If we wanted to see what that wind resource was over a full month, there it is available. What I'm going to do in this example is load an Xarray. So basically in the PyPSA RSA model, we do a lot of pre-processing of our weather data, and then we store it in a netcdf format. This has a few advantages over CSV, but the one is that when you have very big weather files with a lot of data, the CSV files get very slow to load into the model. They also take up a lot more space. So we prefer to work with Xarray, and then Xarray can save directly to netcdf files. So, and in the second kind of session, we'll talk about how we can actually create these raw weather files. But if you look here now, we essentially have an Xarray. So an Xarray, you can just think of it as if you had like a normal NumPy array. NumPy gets very difficult to keep track of arrays when you have multiple dimensions to it. So X-array is just a very optimized way to work with arrays that have multiple dimensions over it. So for example, here we have a time dimension, we have a bus dimension, and we have a parameter called intra-regions, which is the areas that are used in the model that were available. So for example, if I wanted to select time equal to 2012, it's now selected just the year. And if I wanted the bus equal to, I don't remember what it is called. It's by province, so Eastern Cape. Now you can see what's happened is I've selected all the values for Eastern Cape, and intra-region, I'm just going to select in red. So in the red, power corridors and areas that have an approved EIA. So now I have a single set of values, and I can convert that to a pandas data frame. And now I'm back to kind of the same place that I was there. So now we can take our WinPU. If I wanted to plot that same first day again, this is that calculated then wind power profile output. Okay, so I'm just going to load now two random profiles, one for wind and one for solar PV. And then here's just some very basic capital cost information. We're going to assume 15 million Rand per megawatt for PV, 25 million for wind. We're going to have a diesel generator at 4 million Rand per megawatt, and a 1-hour battery and a 4-hour battery for 10 million Rand per megawatt and 25 million. Fixed O&M just set as some parameters as a percentage of capex, so ranging between 2 and 5% in this toy example. And then for our variable costs, our diesel gen set at 6 Rand per kilowatt hour. So just going to run that cell, and now that means again that everything is kept in memory. So now if I look at capex, I have a dictionary that has this mapping of capex. So when you're setting up a PyPSA network, the first thing that you're going to do is establish an empty network object. So you do that with this first line, PyPSA.network, and as you can see now, there's nothing in it. So this is just a container, sort of an object for all our relevant network information. So we've assigned nothing to it, so we have an empty network. The first thing that you're going to want to do is then assign what we call a snapshot. So these are the time steps that the model is going to consider. So we're going to have basically a date range that goes from 2024. So we're going to model 1 year of data, and it's in hourly increments. And then we're going to use our first function that just says remove any leap days from that. So if I run that now you can see our container says that it actually has something in it. It's got 8,760 snapshots. And if I wanted to see what all those hourly snapshots look like, I can print that out and have a look at it. Okay, then I thought maybe an interesting simple problem would be, let's recreate a simple example around the risk mitigation program. So we're going to try to recreate the Kenhardt projects. So we're going to have 150 megawatts combined output. That's our load. And we're going to say that we only want that load between 5 a.m. from 5 a.m. to, I think technically it's to 9:30, but we'll just say it's not. Okay. So now I've added a bus to our network. So it's a single node and it's called grid. And now I've added a load. So now if we can go back and look at our PyPSA network, we can see that now we're starting to populate it with more and more components. And if we wanted to look at the bus, for example, it's buses. Here we just have some default parameters that got set for that node. We don't have any generators yet, but we can look at our load profile that we just came up with. If I set it to a single day, we'll be able to see our kind of targeted RMI triple P profile. So from 5 a.m., we want to get as close as we can to 150 megawatts. And then technically at 9:30, but at 9, we're going to drop that off. Okay, so now the next step is how do we add a generator into the network? So we're going to model PV and batteries in this case. So you don't have to provide all of those parameters that I showed you earlier. When you don't provide an input parameter, the default value is assumed. So here we're going to optimize the capacity. So we want to work out how much PV and battery storage we need to kind of meet that load. So the first thing is that we need to give it this normalized PU profile between 0 and 1. And in this case, you don't have to assign something as with dot values. So this is just taking the numerical data, but you do have to make sure that your columns and your index then match what's being expected for your PV generator. So here I just took the solar profile and I was being lazy, so I just took the values, the first 8,760 values. Again, we need to define our capital cost, and here we're going to use our annuity function plus the fixed O&M, and we times that by the capex, and that's going to give us the annualized cost for our solar PV generator. And then finally, we set pnom extendable equal to true, because that is then we're going to optimize that capacity. So we're going to add our generator, and if we look now at the network again, you can see that we've now added a generator called PV. It's got default parameters for everything that we didn't specify. But for the things that we did specify, for example, capital cost, wanted to look at that. We now have our annualized capital cost that is there for that generator. We're not going to make it a complicated example at this point. So the next thing that we need to add is a 4-hour battery. So for the battery storage, we're saying max hours equals to 4. It's going to happen at the same bus, our bus called grid. And we have efficiency for charging the battery and efficiency for discharging. So here I'm just taking a round trip efficiency of 90% and then splitting that between storage and dispatch. And then finally, there's something called cyclic state of charge. This just means that the amount of energy in the battery at the beginning of the year and the end of the year must be the same. So that's set to true, and then we have our capital cost for the battery, and we're again going to allow that to be extended. Okay, so we've now set up all the basic information, and now what we're going to do is pass it to a solver. I'm using a free solver here called CBC. It's also possible to use a solver called Highs. And basically it's now run and it's come back with an optimization. And we see that it said we need to build 783 megawatts of generator and 300 megawatts of battery storage. So obviously this is well, it's not too much higher, but it's quite a bit higher than what is in the actual ScarTech projects. But there's a reason for that, and it's that we said you absolutely have to meet the load profile in every single hour. So your demand is completely inflexible, which means that we are significantly oversizing our generation and storage to be able to meet that profile. So if we look at then what a dispatch curve would look like, so we've got our load profile here over a day. We've got battery discharging in the morning period. Then we have significant solar, and we have this over generation. A lot of that solar is then being used to charge the battery, and then it being discharged in the evening period. So now, if we were to say, okay, well, maybe there's actually some flexibility in the contracting. So you want to get to a point where you don't have to meet load in absolutely every hour, but if you don't meet that load profile, there's some kind of a penalty. So I'm going to add a generator in here, and it has a negative sign. Sorry, this is excess. Excuse that. Load sharing, this is the one I want. So we're gonna have a generator here, and it's got a very high marginal cost. So if we basically, this is a cost that we have to incur of 20 Rand a kilowatt hour if we breach the rules of the RMIPP. So now I'm gonna just restart. Sorry, there's some code at the bottom that I don't want to run, which is why it's running it sequentially. And now we're going to resolve our model, and we're going to see what difference it made having some flexibility in the contracting. And you can see that now we are at 493 megawatts, and our battery is still at about 290 megawatts. So this isn't actually too far off what the actual system design is, I think, for this SkyTech project. So I think it was 540 megawatt design and about a 225 megawatt 4-hour battery. So just with playing with a few numbers, we were already in the same ballpark. And obviously, I just picked kind of a random solar profile, and the load shedding isn't aligned exactly to the contracting. So we're already kind of now in the same region. And if we were to plot that, you can see here's kind of some time, for example, and where we're not fully meeting the load profile. Of course, you can then add a lot more complexity to the model. So if you wanted to add, for example, a diesel genset, and we wanted to do a mix of solar and wind, again with a kind of profile in a random area. So now it's optimizing multiple generators. It's not just solar, PV, wind, and battery. So now we have wind. We see our solar has come down a bit. We've got about 64 megawatts of wind and 33 megawatts of solar. And our battery storage has come down a bit as well. And then if we look at what the dispatch looks like, we can see that we have some wind in the kind of early morning period that's being used to charge the battery. And then we have some kind of dispatch that looks like this. Sometimes what you'll see in your dispatch profiles that come out of the solver is you might see some of this kind of where it's a bit of a sawtooth. That's typically a numerical issue. And it's just the fact that there's no cost for when the battery gets charged or charged and then stopping charge and then charging again. So as far as the optimization concerned, that's exactly the same as if you were to charge it at half, for example, over that period. And that's it. So this you can see within a few clicks of a button, you can already get a feel for how a simple network might operate. And now you can even test things like, okay, well, what if there's a value for excess energy? So at the moment, if we run it with no value for excess energy, you can see that we basically get almost the same answer. But if we say 1,000 Rand a megawatt for excess energy, You can see now we have a totally different story in our optimization. And instead of curtailing all that energy, what we see is a massive overbuild of renewables, because we said that we could sell any energy up to 1,000 megawatts at 1 rand, and that 1 rand was we were getting paid more money than the PV was costing us. So that's why we've totally overbuilt like that. Okay, so the final kind of step in the demo, and then I think we can maybe take a 10 or 15-minute break, and I'll answer. I see, Greg, you've asked a few questions. Essentially, just to demonstrate some of the flexibility that you have within PyPSA and using some of the backend. So it's built on something called LinoPy, which gives you a very flexible backend where you can actually modify the equations and the constraints that in the model very easily. So, for example, we've now built our model, and if we wanted to see what does that PyPSA model actually look like, well, we see that we have some different variables that have been defined. So we have the generator capacity that might be optimized, the storage capacity, we have the generator power in every hour, and then how we charge the storage and what the state of charge is on the storage. So for example, we're going to write now a custom constraint that does something very silly, but just to show the example. So I'm going to just get rid of the excess sales. Okay, so now what I'm going to do is I'm going to say between 12 o'clock and 1 o'clock, we want to say that PV can't generate any energy. And we're going to write a custom constraint that does this. So the first thing is we're going to define the hours. So we're selecting all the snapshots where the hour is either 12 o'clock or 1 o'clock across the year, and we see we have 730 hours where that happens. So now we take our variables and we're saying we're going to take the generator power and we're going to select the generator that's called PV, and we're going to say over the snapshots for those 730 hours, we're going to force the power to be 0. So even though there's resource available there, we're going to force it to be 0, and we're going to add our own constraints into the model. So now you can see it's added a constraint, and it's saying it's found all of those examples where the PV generator is between 12 and 1 o'clock, and we've said that the power must be equal to 0, essentially. So now we're going to resolve the model with this custom constraint in it. And if we go back and we plot our results, now you can see this weird story, but basically what I've said was that I forced the PV generator, to make no power between 12 and 1, and you can see that that's exactly now what's happened in the model. So this kind of backend allows you a high degree of flexibility to just add in all these kind of custom constraints and how you can force the model to do different things. Obviously, this is a very simple toy example, but essentially in the more complex power system models, and for example, if you want to be modeling hydrogen and different constraints around how that performs, having this ability to easily have custom constraints is very useful. Finally, just before I take questions, is you can actually access the constraints itself if you wanted to see what PyPSA is actually doing under the hood. So the nodal balance, for example, we can pull out here, and these are the exact equations that get written to the solver. So you can see it saying for the first hour, it's got to add the generation from the wind. It's going to add the generation from the PV, the diesel genset, load shedding, any storage that's being dispatched. It's going to subtract any storage that's charging, and the supply and demand has to balance. Well, that has to meet a load of 0 in that hour. And then we had some other hours where after 5 o'clock, the supply had to be equal to 150 megawatts. So this is just telling you kind of what's going on under the hood, and you can do a lot of exploring. Understanding LinearPy does require a little bit of a back-end knowledge about how Xarray works, for example. So it does take a little bit to get your head around, but once you've done that, it's easy to deal with. So yeah, I hope this simple example gets you up and going. We'll provide all these files so you can play around with this in your own time. Just to show you kind of a very simple PyPSA script, and then we can get into the kind of some of the more detailed scripts around PyPSA RSA. Greg, your comments. So are netcdf files already processed into per units? What is that? Well, they actually raw weather data like wind speed. Yeah, so what we have and kind of what I'll walk through now is a set of pre-processing scripts, and those scripts will basically take in all the weather data. They're going to pre-process that. It's going to go through a model that's then going to estimate the power output, and then it's that unitized power output profile that then goes into the next step of the actual optimization. So we provide a set of about 5 or 6 different notebooks, and each of those notebooks will take you step by step how you can start to access data from Era 5, from Sarah. We also have data from WASA, as well as the NREL NRSDB, the National Solar Radiation Database. So some of that is not, all the input data is quite a mission to get. So for example, Sarah is quite a large data set. So it's not as user-friendly to work with as Era 5. I think our Sarah dataset that we've downloaded sits at about 60 gigs. Whereas the Era 5, you can get a cutout that's just a couple of gigs, for example. Highs. Yeah, so our experience is that the open source solvers remain significantly behind the commercial solvers.